You've probably heard it by now, an AI that can perfectly clone a voice from just a few seconds of audio. It honestly feels like magic. But what if I told you that behind that magic is this incredible engineering story, a journey of solving one problem just to uncover an even harder one? Well, today we're going to pull back that curtain and trace the exact path that took us here.
So that's the big question, isn't it? How in the world did we leap from those glitchy, robotic text-to-speech voices of the past to AI systems that can now generate audio that is, well, literally indistinguishable from a human? To get that answer, we have to start with the first major wall that developers slammed into when they tried to scale this stuff up.
And that wall has a name: the AI voice dilemma. See, for the longest time, the fundamental way we were even trying to generate speech was, to be blunt, broken. It created this hard ceiling on quality that everyone in the field just couldn't seem to break through.
Okay, so early models, like the famous VAL wallet, they basically borrowed their whole strategy from large language models. They take a smooth audio waveform and chop it up into a long series of discrete numbers, or tokens. Then they try to predict the next token in the sequence, one after another, to slowly build the audio back up.
And this is where it all fell apart. Just a 10-second clip of audio could turn into thousands of these tokens. So if the model makes just one tiny mistake on, say, token number 5, that error snowballs. It affects token 6, which then messes up token 7. It's a domino effect. You get these voices with weird rhythms, they'd skip entire words, it just sounded bad. And here was the real kicker, the dilemma. If you tried to use a better audio codec to get higher quality sound, it just created more tokens, which made the error problem 1,000 times worse. You were completely and utterly stuck.
So how do you solve an unsolvable problem? Well, you don't. You change the rules of the game. And that's exactly what happened with the first big breakthrough, which came from a system called Natural Speech 2. It just took a completely different path.
This table lays out that massive shift perfectly. Look at the first row. Instead of those clunky, discrete tokens, Natural Speech 2 used what are called continuous vectors. They hold way more information without creating these insanely long sequences. But the real game changer is in that second row. They completely tossed out the old, error-prone, autoregressive method and swapped in a diffusion model. That one change made everything incredibly stable and way, way simpler.
So what's the difference really? Okay, think of the old autoregressive way like building a chain, one link at a time. If you make one weak link early on, the whole chain is compromised. A diffusion model, on the other hand, is more like a sculptor. It starts with a big random block of noise and then refines the entire thing at once, in parallel, carving away until a final, perfect audio emerges. It's just a much more robust way to build something complex.
Now, to make this whole new approach work, you need data. A lot of data. The Natural Speech 2 model was trained on a staggering 44,000 hours of human speech. You need that kind of scale for the model to learn the sheer variety of human voices, tones, and rhythms out there in the world. And just like that, Natural Speech 2 had cracked it. The audio was stable, the quality was high, it worked. Problem solved, right? Well, not quite. Because solving that first glaring problem only revealed a second, much more subtle one hiding underneath. The problem of control. And this is where things get really fascinating. We're now at the next big frontier in AI voice, which is called the disentanglement challenge. You see, in a real human voice, all its different qualities are kind of tangled together, and the AI models had no way to pull them apart.
Disentanglement is basically what it sounds like. It's about deconstructing a voice into its core building blocks. You've got timbre, which is the unique texture of a voice. Think Morgan Freeman versus Christian Schall. Then you have prosody, which is the rhythm, the pitch, the emotion. And finally, you have the content, the actual words being said. For true control, you have to be able to tweak each of these knobs independently.
I mean, think about it. How can you ask the AI to make a voice sound more excited by raising its pitch without accidentally making it sound like a completely different person? If timbre and prosody are all tangled up in the AI's brain, you can't. You adjust one and the other goes haywire. Solving this was the key to unlocking truly expressive, controllable AI speech. And that is precisely the problem that Natural Speech 3 was built to solve. It introduced this brilliant strategy called a factorized approach, which is really just a fancy way of saying divide and conquer.
The whole process is actually pretty elegant. It happens in 3 steps. First, a brand new codec they built, called FacCodec, literally pulls the audio apart and sorts it into different buckets for each attribute.
Step 2, a specialized diffusion model generates brand new attributes inside each of those separate buckets. And finally, the codec puts all those new pieces back together into one seamless high-quality waveform.
Okay, so take a look at this diagram from the paper. This is step 1 in action. On the left, the raw audio goes into the encoder. Then, watch as it gets split into 4 different paths. You have a timbre extractor, which figures out the unique vocal signature of the speaker, and then separate streams for prosody, the actual content, and all those tiny acoustic details. This right here is disentanglement.
And the generation part is just as methodical. The model doesn't just create everything at once. If you follow the diagram, it first figures out the duration, like how long to hold each sound. Then, based on that, it generates the prosody, the rhythm. After that comes the content, and finally, it layers on the acoustic texture. Each step builds on the last, which gives the system an insane amount of fine-grained control. So, with this new factorized architecture that could handle both stability and control, what were the results? Well, this is where the journey leads to something pretty mind-blowing.
First, they scaled everything up. I mean, way up. Remember how Natural Speech 2 used 44,000 hours of data? The biggest Natural Speech 3 models were trained on 200,000 hours of speech. That immense scale was absolutely critical for the model to truly master all those subtle, disentangled attributes. And the model itself also got huge. The largest version of Natural Speech 3 has 1 billion parameters. That's the kind of computational firepower you need to not just imitate human speech, but to actually replicate its deep complexity. So, what did all that scale and clever architecture actually achieve? Well, here's the money quote directly from the research paper. For the very first time, an AI model achieved human-level quality on a really tough benchmark. This wasn't just good for an AI. In blind tests, people could not tell the difference between the AI and a real human recording. And it did this zero shot, meaning it can clone a voice perfectly from a short sample it has never ever heard before.
So let's just recap that whole journey. We started with these old-school systems that needed perfect studio recordings. Then came the first big, messy models that could clone voices but were super unstable. Natural Speech 2 came along and fixed the stability problem using diffusion. And finally, Natural Speech 3 tackled the control problem with its divide-and-conquer approach, and in doing so, it pushed the technology right across the finish line to human parity.
And that journey leaves us right here with one last massive question. This technology is the result of years of brilliant people solving incredibly hard engineering problems. But now that they've solved them, now that a machine can generate a voice that you or I cannot distinguish from a real person, we have to ask ourselves, what even is the boundary between synthetic and real anymore? And who gets to draw that line?